So first, to find the frequency, there really, when you're asked for frequency, there are kind of two ways to think about doing it. Either it's easy to find the period and you can solve it from the period, or it's easy to find omega and then you have to go from omega. In this case, we know the spring constant and we know the mass, so it's easy to find omega. And so we'll have to go omega to the period to the frequency. So omega is equal to the square root of k over m, so square root of 100 over 0.75. And you get a value of 11.54. What are the units of omega? It's 1 over seconds. I like the effort. 1 over seconds. And one thing to remember is 1 over seconds is hertz, but don't use hertz for this, just so we can keep omega and frequency separate. Okay, so frequency will use hertz, omega will use 1 over seconds. And then from here, we know that the period is equal to 2 pi over omega. So you get 0.544, and what are the units of period? Seconds, yep. And from there, the frequency is 1 over the period. So you get about 1.84, and the units of frequency is hertz. And B, to get the maximum speed, you know, both A and B, it doesn't matter whether the spring is horizontal, vertical, at an angle, whatever. All these calculations are just the same. So V max is just equal to the amplitude times omega. What's the amplitude? What? Well, actually it's 0.1 because it's how far it's pulled from the resting length. But notice that the full distance that it would travel in the oscillation is 2 times that period. You know what I mean? But the distance that it's pulled from the equilibrium position is the period. So this is going to be 0.1 times the omega that we just calculated, 11.54. And so you get 1.154. And what are the units of V max? Meters per second, yep.
I'm sorry.
Yep.
So it's not 0.15?
No, 0.15 was that starting length of the spring. The 0.1, it says hanging vertically, the mass is pulled 0.1 down from the equilibrium position. Oh, so you need that. And then now we're trying to figure out where that occurs. So I'm going to draw a picture with gravity off and one with gravity on. Okay, with gravity off, the mass hangs right here at this distance of 0.15 meters. Okay. With gravity on, it hangs a little bit lower. So this distance is 0.15 meters. And the distance from there to here is mg over k. So that's 0.75 times 9.81 over 100. And that is 0.074. So the total distance from the ceiling, and this equilibrium position is also where it's going to be at its fastest. It's where it's going to reach that maximum V. And so Vmax occurs 0.15 plus 0.074, which is 0.224 meters below the ceiling. And how do I know that that in ceiling we have an E first and then an I?
Before you accept that.
Yes, that's how. Very good. I'm just trying to help you be well-rounded people. Any questions about this?
So the 0.074, that's the mass of the.
This is mg over k.
Yeah.
So the 0.75 is the mass, yeah. And now the oscillation is going to go, so from this position, it's going to go up 0.1, down 0.1, like this, right? So this distance is 0.1 meters, and this distance is 0.1 meters. And so how do we get the farthest this ever gets from the ceiling? What? Yeah, that's right. So it's just gonna, the farthest it ever is from the ceiling is the resting position plus another 0.1 meters. So D is 0.224 plus 0.1, so 0.324 meters. Any questions about any of those? Yep. Yeah.
Capital A, that's just that is the distance that we're told, like a change, right?
Yeah. The amplitude is the distance from the resting position to the extreme position. Yep. Any other questions? Okay, there's one other type of simple harmonic motion that you'll have to do a couple calculations for. And so one other type of simple harmonic motion, and that is a pendulum moving through a small angle. Okay, so the small angle part means going through a motion like this is okay for our calculations, but something like this, our calculations would give really bad results. Okay. And a good value to use is like a cutoff angle is 15 degrees. And In calculating angles for pendulums, we use radians instead of degrees. So 15 degrees is 0.26 radians. Okay. And, you know, it's not like a cutoff is kind of a bad way to think about it, because what it really is the results get better the smaller this angle is, and they get worse the bigger this angle is. But 15 degrees keeps the way we're going to calculate it within, I can't remember if it's within 1% of the correct answer or within 5%, but something like that. Okay. So for a pendulum, all previous simple harmonic motion equations work, except now P of t is the angle of the string from vertical in radians. And that means that the speeds, so V max and V of P, are angular velocities. In units of radians per second. And the last thing is, you can calculate omega again, but obviously you can't use square root of k over m because there's no k here. And it turns out that this might be a little surprising, but m doesn't matter. Whether this is 100 pounds or 1 pound, it doesn't have any effect on the behavior of this pendulum. Omega is calculated as the square root of g over L, where g is 9.81 meters per second squared, and L is the length of the string. Okay, so applying what we know about the mass spring system, how will the frequency, so say that we're ignoring everything outside of that cutoff, okay? So everything that I'm talking about are angles between, so starting it at, say, 14 degrees from vertical, and then separately starting it at 1 degree from vertical or something, okay? How does that angle, that starting angle, affect the period of this motion? That definitely is what you would expect to happen. But if you think about it in terms of all the equations we have, those times will be the same. It'll take the same amount of time for, if you hold it out to 14 degrees and let it go, it'll take the same amount of time to do its motion as it will if you pull it out to 1 degree and let it go. That seems a little weird, but the way it works is kind of the same way the spring mass system works, that those periods stay the same whether you pull it a long way out or just a little way out. If you just pull a pendulum out 1 degree, you know, in order for it to pick up speed, part of gravity needs to be going in the direction of its path. And if you only pull it out 1 degree, gravity isn't working very much in the direction that it's going. And so the net result is it's going really, really slowly. And you can probably sort of visualize that. If you just barely pull something out, it'll just go through this motion so slowly. Whereas if you pull it out to 14 degrees, it'll get going pretty fast, you know. And so that's how those end up. It turns out they're exactly the same. And even with our approximation, the answers would come out really close. Have I?
Yeah.
I had to do that in, yeah, we should do it. We'll do Mythbusters. I had to do that in physics lab when I took physics 1.
It just sounds like it would just be so impossible.
Yeah. Okay. Well, we'll do it.
All right.
All right. We'll do it in lab on Friday.
All right, cool.
We'll cut out some other stupid thing and do that.
Yay.
Okay, so I have one example problem I want to do with this. Okay, so say you are assigned to pick up the Queen at the airport. So you have to pick up the Queen, or Queen, that's even better. You have to pick up the band Queen. I'm sure they are probably still a band and they just have some new singer who is in a tribute band or something. Let's say it's at 3:30 and your watch broke. Oh, speaking of that, did you know that Brian May, the lead guitarist for Queen, has a PhD in astrophysics? Yeah.
You realize he missed his calling after the astrophysics bit and wanted to sing a song.
Well, he did all that after, or like while he was doing the band stuff. And yeah, he's like a professor of astrophysics, but he still does like world tours and stuff. Yeah. And his guitar that he plays, he made himself with the help of his dad when he was young out of telephone parts. The guitar that he plays in like Wembley Stadium and stuff. Yeah. Yeah. Okay, so what are you going to do? You don't have a watch. You have to pick up Queen. You can't be late. They're British, so they probably don't tolerate lateness. So your idea is you're going to take your broken watch and put it at the end of a string and use that as a pendulum that you're going to use to, you know, yeah, there's probably other solutions. But those other solutions aren't as relevant to what we're talking about. So what you want, though, is in order to do this, you need to know what the period is going to be of the motion. And even better yet, you'd like to make it a period that makes it easy to figure out the time. So let's do 1 second. And you're just going to sit there and count to 6,000, whatever, you know. So how long should the string be so that you get a period of 1 second? Okay, so does anybody have like a rough idea of how to do this? Like, what can we solve for? What direction can we go to get this? That's right. So we're going to use the fact that the period is 2 pi over omega, and omega is variables that we know. And the algebra will get a little messier than the other ones, but yeah, we're going to solve for L from the fact that, so we know that omega is equal to square root of g over L. And we know that the period is equal to 2 pi over omega. So we can combine those two. Like if we just plug this expression for omega in the period equation, we get that the period is equal to 2 pi times the square root of L over the square root of G. Any questions about the algebra on that? And so the period is 1 second. We have 1 second is equal to 2 pi times the square root of L over the square root of 9.81. Now you can square both sides, and you get 1 is equal to 4 pi squared times L over 9.81. And so L is equal to 9.81 over 4 pi squared. And if you solve that, you get 0.248 meters. So a quarter of a meter. Any questions about that? Yep. It would affect, okay, so it would affect some things like this. The short answer is no. Like you would think that it would, but it doesn't. The long answer is, yeah, it would have a little bit of effect because some things like we're assuming that the string has no weight, and if the closer the mass and the string are to the same weight, the less you can make that assumption. So in that sense, it would a little bit. It would make this calculation a little worse as that mass got smaller. And the other effect it would have would be the effect of air resistance would be bigger. So your results, like this approximation is a better approximation as that mass gets bigger. But as long as you can make the assumptions that you can neglect the weight of the string and you can neglect air resistance, then no, that mass doesn't come into it. Any other questions about this? Okay. So the next thing we're going to talk about is waves. That's all we're going to do in harmonic motion. And you can think of waves as a traveling let's say progression of oscillations. But a key thing about waves to remember, and this is an easy thing to get wrong with your intuition, is that waves carry energy, they don't carry material. In other words, like what a sound wave does, as an example, is when a sound wave travels, air molecules here vibrate, and then air molecules next to those vibrate, and then air molecules next to those vibrate, okay? And it's that succession, not succession, succession of vibrations that carries the wave, okay? But what doesn't happen is vibrating air molecules here travel the whole way, you know? like if you put a little bit of, some kind of colored thing in the air here, that color wouldn't travel. It would just vibrate briefly until the energy moved on to the next part, okay? That makes sense if you think of what it would mean if waves actually carried material from one place to a next. So here are some things to keep in mind to kind of remind yourself to think about this the right way. Sound waves sound waves move really fast. If sound waves carried material, every sound would go along with a 750 mile per hour wind, because that's the speed of sound, and that doesn't happen, right? I bet it would get old pretty quickly. 750 miles an hour is really fast. Like tornadoes, aren't they like 200 miles an hour? Well, yeah, you would guess that. Yeah. The speed would still be the same, just more molecules, I think. But yeah, right. It wouldn't be good, I don't think. Sound doesn't produce 750. And another example is, when you take the end of a jump rope and flick it, and you see the wave travel along, that's a wave. And from experience, the wave moves without the jump rope coming out of your hand, So the wave doesn't carry the part of the jump rope that you're holding, So a flicked rope doesn't fly out of your hand. Okay, so whenever you get turned around backwards on this, think of those two examples. And it's easy to think about this wrong. I sometime recently, like I was reading an interview with a really famous, like well-known guitar builder who makes $15,000 guitars, like these beautiful instruments, and obviously knows everything there is to know about producing sound waves from a piece of wood and strings and stuff, But he said at one point in the interview, well, the thing to keep in mind is a guitar is really just an air pump, And I read it and was like, huh. And then I was like, wait, that's not true. It's not an air pump, A guitar makes air molecules vibrate, but an air pump actually takes air molecules here and puts them over here, And so that's not what a wave does, And so even people who think about this stuff all the time, it's easy to make this mistake, confuse these two things. Yeah, right. I mean, okay, so because of this, so as a consequence of this, or like one practical application of this, is I'm going to tell you something that many or all of you have done at some point, and it didn't work, and I'm going to tell you why it didn't work. So here's the shore of a lake or a pond, and here's the water, and here's you. Yeah. And you're not happy because this is your Frisbee. Okay? And so your Frisbee goes in and you're like, damn. How am I going to get that thing? And so you have this great idea. I know you've done this. I know Rob's done this.
Of course.
You're like, oh, I have the best idea. I'm going to take this rock and throw it.
Everyone's done that, though.
Yeah.
Not smart enough to do that.
You would, yeah. 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 So you're like, I'm going to throw this rock to the other side of the frisbee, and then that's going to make water waves that come to the shore, and the water waves are going to carry the frisbee back to shore. You know? It totally makes sense. But you do it, and you get very unsatisfying results. And the reason, and I mean, I bet I've done this 50 or more times in my life, like, because it just like has to work. But the reason it doesn't work is because those waves don't carry water molecules. They only carry energy. So what happens is the wave goes by the frisbee. The water molecules oscillate up and down, and then the wave passes by and the frisbee hasn't gotten any closer. Like the water touching the frisbee, all it does is go up and down. What travels is the oscillation from those molecules to the next molecules to the next ones. So, so now, like next time you're playing frisbee and your friend is like, throw that rock in, yeah, you can just be like, you are so dumb. Yep.
One question though. What about like in the case of tsunamis at the edge, like when you get to the coast?
Yeah.
So how does that work?
Okay, so yeah, like the surf or whatever, the tides, it gets complicated because so a lot of the behavior of the tides comes from the interaction with the wave, with the shore, the ground below. And so that creates like a rotation, and that rotation makes some things happen. But just these straight up and down waves, if you ignore the effect, and for little waves, there's not going to be much of that interaction with the ground. Yeah, it's sort of what you're talking about is a real effect that that comes from the interaction with the ground. Anyone have any questions about that? So I'm going to just stop there. That's the lead into waves. They carry energy from molecule to molecule, but they don't carry molecules.
But you can get your frisbee back if there's a tsunami.
Yeah, I think that's a good question. Well, I don't really know. I'd have to.
No, you won't. It's like, 'cause I heard, like,
I think the thing is, so like surfing, the way that works is you swim to get up to speed until you're going the same speed as the wave roughly. And at that point, the wave lifts you up and you're basically just sliding down a ramp. It's not that the wave is really pushing you, it's really just gravity that you're like sliding down a ramp that's been made by the wave.
It's a better chance.
Big enough wave and then put the frisbee on it.
But yeah, you'd have to, it wouldn't, yeah, you'd have to get the frisbee up to speed. So you'd have to go out there, swim the frisbee up to speed, and then at that point you might as well just bring the frisbee in.
Target. You don't lose it.
Yeah.